Yeah, so today we're going to talk about the concept of state functions, and it's nothing. It's something that's probably not going to mean much to you until we do this exercise. And so, here's the background of what we mean by state functions. There's things called inexact differentials, and Q and W are not state functions. And sometimes you'll hear some people say that incorrectly. They'll say work is a state function, but work is not a state function. What do we mean by what's the importance of that fact? Well, because they're not state functions, they have inexact differentials and cannot be simplified to delta Q and delta W. Notice you'll never see that in any of my terminology of a delta Q or a delta W, because Q and W are by definition deltas. They're by definition heat flow or work delivered or work done on the subject. A substance doesn't have an amount of work. A substance does work or has work done on it. So that's like saying, how much Venmo do you have? It doesn't make sense, right? Venmo is a transactional process, just like work and heat. You could say how much money you have, and that's like energy, capacity to do Venmo. So energy is the capacity to do work, money is the capacity to do Venmo or to do cash or to do credit, those kinds of transactions. And so work and heat are transactions. So their integration is path dependent, and we'll see an example of that. We're going to go out in the hall, and we're going to walk up the stairs and go up the elevator and do different kinds of paths, and then we'll talk about the difference between work, heat, and energy. So those things that have exact differentials are energy, pressure, volume, temperature, enthalpy. These are all state functions, and therefore their derivatives are exact differentials. And that also means that they can be simplified to delta U's, delta P's, delta V's, delta T's, delta H's. So we'll see those deltas, and those are easily calculated of final minus initial, right? So you don't have to know the path. So that's the big difference. Their integration is not path dependent, therefore we can just take the endpoints, the final minus the initial, and get the deltas. So the exact differentials are simplified to deltas. And so the end result is most integrals can be simplified. And we'll have a whole set of conditions. Like if you look at a problem and you say, okay, let's think about these conditions like isothermal conditions or constant pressure, isobaric conditions, then you can have ways to calculate the work and the heat using the exact pieces, the state functions. So we'll be able to get to work and heat and not have to really do a lot of integration. We'll use the delta factors, the exact differential pieces, the state functions, to calculate our work and our heat. Okay, so let's go ahead, and I'm going to stop the video. We're going to go out in the hall. We're going to do a little exercise. Yeah, okay. So this morning we're going to be doing an exercise talking about state variables, all right? And again, state variables are path-independent variables, okay? So things like energy, temperature, pressure, and so on. And so you were complaining about the stairs, so you can take the elevator. Yes. Okay, you go to the third floor, you go to the second floor. Okay, y'all can go now. All right, I want you to, you came late, so you're going all the way to the third floor on the stairs. Gotcha. Okay. Oh wait, she went on the stairs, so you can go to the third floor on the elevator. You're going to the third, you're going to the second floor on the elevator. Second. Okay, and then you can go to the second floor on the stairs. Okay, and you guys can stay right here. No. All right. Sitting. Okay, Danny, you go all the way to the third floor on the stairs. Let me get you guys in the frame here. So way up there at the top, these folks here, they took the elevator. One took the elevator, one took the stairs, and assuming they have the same mass, they have the same energy, right? But they took two paths to get there. Right. So did you catch that? You have the same energy even though you took two different paths. So one of you did more work than the other. The one that took the stairs exerted themselves more and did more work than the other. So the work is different, but the energy is the same. Do you see that? And the same for the second floor. Y'all have the same energy. One took the stairs, one took the elevator, two different works, two different heats, the same energy. And y'all have the same energy.
Nice.
And so we could calculate this. If we knew everybody's mass, we could calculate gravity. So we really are talking about energy. You know, your potential energy at the second floor doesn't matter if you came down from the third floor or came up from the first floor. You see how energy, it just depends upon what your state variables are. And in this example, your most important state variable is elevation, because gravity's pulling on you. So do you see the difference between the path-dependent work variable and the state-dependent energy variable? Okay, let's go back. Okay, so with that little exercise, we understand now the difference between a state function and a non-state function. So these inexact differential pieces are not state functions. So the stairs and the elevator are ways to change your energy, like adding heat or doing work. Those are ways to change the energy. And so I like to think of them as elevator or stairs. Or if we're talking about cash transactions, you know, it could be check or Venmo or credit card. Those would be ways to change your money, but they're not money themselves. And then the state functions are changes in energy, changes in temperature, pressure, volume. Those are your state variables. We can do the same thing we did out there with the elevator and the stairs, just doing total differentials. So we could see how the pressure changes if we look at the derivative with respect to volume and the derivative with respect to temperature. So this is what we call an equation of state. It's a pressure equation that is a function of volume and temperature. So you know these, you know what an equation of state is because you've been using one since your freshman year. That would be the ideal gas law. So you see that pressure equation is a function of volume and temperature, assuming the moles are constant, right? And now this is it's written this way a lot of times with the molar volume. So that's the volume per mole. And so you see that if volume's in the denominator and moles is in the top, that's still volume per mole, right? The per mole comes up to the top. Yeah. So that's why you see this little lowercase m here in the subscript. That's molar volume. So here we are. Clearly, this is a pressure equation that's a function of temperature and molar volume. So if we're going to do what we call a total differential, we want to take the derivative with respect to all of the variables, all of the things that can change. And so in this equation, there are only two things that can change, the temperature and the volume. But you might imagine which one do you do first, right? Should you do the derivative with respect to volume first and then temperature? Since you have two variables, you have a choice, right? Or do you do the slope with respect to temperature first and then the volume derivative? So you see how you could have a choice. If you have two variables, you can do the derivative with respect to the one and then another, or vice versa. Okay, and that's what we mean by exact differentials. We're going to show that it doesn't matter. Okay, so do y'all know what these little funny D's are for the derivatives? Yeah, it's the derivative, but this is the partial derivative. And so instead of like d by dv, these are funny D's. They're like what I call D's in a windstorm. The little top is being blown back. All right. So these are partial derivatives. And what we're doing is we're taking the derivative with respect to volume, but we're holding temperature constant. So we're pretending on this first one that temperature can't change. And then later we'll do the derivative with respect to temperature, assuming that volume can't change. So that's a nice way to do these derivatives. It makes things very simple. Even though we have two variables, we're going to treat them one at a time. And we're going to assume when we're taking the derivative with one, we're going to assume the other one is constant. So this is pretty easy. We can substitute that ideal gas law in here. And so now this is pretty simple. We're taking the derivative with respect to volume, and volume's here in the denominator, with holding temperature constant. So this is a V to the minus 1 power, right? It's in the denominator, V to the minus 1. And so the simple like polynomial derivatives, you just pull that exponent out front. So it's V to the minus 1. So we pull minus 1 out front, and then we drop the exponent by 1. So it's going to go from minus 1 to minus 2. So that's what we do. You see here the minus 1 comes out front because it was V to the minus 1, so that's there. And then now it's V to the minus 2. So in the denominator we have V squared. So a little bit of review of your differential calculus that you had years ago. Yeah, exactly. Okay, so we're done with this derivative with respect to volume. Now we got derivative with respect to temperature, leaving volume constant. And so we look at this, is temperature to the first power. So we bring that 1 out front, it doesn't do anything, and then we take it from the first power to the 0th power, and so temperature disappears. Okay, so we're sloped with respect to temperature to the first power, we get minus R over V squared. So we've done the total differential of this. That's how pressure changes with respect to volume and temperature. Okay. But what if we had made the other choice? Okay, what if we had chosen to do temperature first? You see the temperature is first and then volume. Over here, volume was first and then temperature. Okay, so let's do this whole thing again, but start with temperature. So we're looking at the same equation. Again, temperature to the first power. So it goes away, and we have R over Vm. And now we take the derivative with respect to volume. It's V to the minus 1. So minus 1 comes out front, and we have V to the minus 2. So we have minus R over V squared. Look, they're the same. So that's another feature of these state functions, is that they are exact differentials. You can do the total differential with respect to all the variables that change, and you get the same answer no matter what order you do the differentiating. Okay, so that's the order of differentiation does not matter. It's just a brute fact that I'm telling you. We're not really doing anything with this, but I'm just showing you that this is one of the features of these state functions. Okay, but we are going to explore a lot of these little derivatives because some of these things have physical properties that we can measure. Okay, so let's look at a list of them. These are some important thermodynamic qualities or quantities that we have. One of them is the volumetric expansion coefficient. So this accounts for the change of volume with temperature. Now this one is really important for dentistry and for glass cookware. So what would be important for the volumetric expansion coefficient? Why would that be important for dentists? Yeah, what happens in your fillings if you drink something cold? If they shrink when you drink something cold or expand when you drink something hot, what's that going to do to your mouth? Wow, yeah, right? It's going to push on that nerve, or you're going to have some severe pain if you have a filling that really expands with hot or shrinks with cold, because those nerves are right at the bottom of your teeth, and if your teeth change dimension with temperature, you're going to feel it a lot. Okay, same thing with like the Pyrex glassware, like our beakers or cookware, the glass cookware. If you put that on a hot stove, think how hot the bottom is, and the top is not that hot. And so if the bottom expands and the top doesn't, the glass is going to shatter. I mean, think about our beakers. That's pretty crazy. We've got a beaker here, and we've got a flame underneath it, and if the bottom expands and the top doesn't, it's going to shatter. And so they've looked at, that's what makes Pyrex glass and some of these other kinds of glasses for lab glass really high quality, is that they have a very low volumetric expansion coefficient. So they've engineered their glasses for labware and cookware so that they don't have a large volumetric expansion coefficient, because if they did, the bottom would expand and the top would not, and you would create stresses and it would burst. Okay, let's look at isothermal compressibility. So this accounts for the volume change with respect to pressure. Now this one is very important industrially for hydraulics. So like if you're going to be pushing, like you've got a backhoe and you're going to, push this big arm around and dig up a bunch of dirt, or if you got a tractor with a bucket on the front, you're using hydraulics. Now, what's the purpose of hydraulics? You push on this fluid and you push it through a tube and it pushes on a piston. So you're able to deliver force, through tubes long distances away. What would happen if you pushed on that fluid and instead of transferring the force to the piston, it just shrank? It wouldn't transfer the force. You'd be able to pump force into that fluid and it wouldn't do anything. It wouldn't lift the arm. It wouldn't push the bucket. It wouldn't do what it's supposed to do. So for hydraulic fluid, you want to have a fluid that's not compressible. You push on this end and it pushes on that end through the tube. So hydraulics would need to have a small isothermal compressibility. You want your hydraulic fluids to not be compressible so that when you push on this end, it pushes on that end. And in fact, all of your brake systems in your cars are hydraulic brakes. You push on the pedal and it pushes on the fluid, and the fluid pushes on the brake and pinches on the disc brakes or pushes out on a drum. And so you want your brake fluid to not be compressible, because otherwise you'd have a real spongy brake pedal. You push down and you have to push this far and the brake, doesn't do anything. So then we have the Joule-Thomson coefficient. This is the change in temperature with respect to pressure. So if we drop the pressure, we would see a change in temperature. And this is important for cooling, for heating and cooling, for heat pumps, but we really focus on like refrigeration. So if we drop the pressure, we want the gas to cool down. And if the gas cools down, we can use that cold gas to cool our ice tray and make ice. Keep our ice cream frozen. So we'll talk about that too. And then internal pressure. This accounts for the attractions and repulsions in a particular volume of liquid. And this one I use a lot because this is, again, energy per volume. So we're going to deal with this one, and in our lab, we're going to be calling them the Hansen solubility parameters. So it's the amount of energy you have in a particular volume of liquid. And so if you can drop that energy by putting a solute in there, then that solute will dissolve. If that energy goes up when you put a solute in there, then it won't dissolve, because nature wants to go to lower energy. So if I can drop the energy in a given volume by putting a solute in there, then it's going to dissolve. And what do you think happens in water? So you've got water, you've got hydrogen bonding. That's a pretty strong association, but Coulombic attraction is even stronger. So if I could put salt in that same volume with the water, then it spontaneously dissolves that salt. In fact, dissolving salt is so spontaneous that if you put DI water in a metal container, it will strip the metal out of the container. Yeah, they call it aggressive water. Water wants salt, cations, and anions so bad that it will strip the metal out of a container. If it's DI water in a metal container, it will pull it out of the container.
So I could pour.
What's that?
I could pour DI water in just like a normal metal bottle, and it'll strip it of water.
It'll strip the metal cations out of the metal. Yeah, not a lot. Like it's not going to burn a hole in it. Over time it probably would. But yeah, it's pulling. Water will have cations in it. It will make it happen. So if you put it in a metal container, it'll pull the metal oxides and the metal out of that container a little bit. Yeah, it will leach that metal into the water. So you definitely don't want to store like water, DI water, in a lead container. It's going to steal that lead right out of the pipe. And back in the day, it had lead pipes, and they didn't really have DI water, but still, water would leach that lead out of the pipes, and they would deliver the water with these lead pipes. And the royals in those castles that were the first to have running water using lead pipes got cuckoo, yeah, because they were drinking leaded water.
That explains so much.
That's right.
Everyone just had lead poisoning.
Lead poisoning. That's right. Yeah. So let's go through these one at a time and look at some values. Yeah. So this accounts for the change in volume with respect to temperature. Okay. It's beta. Typically, sometimes it's alpha in some books. Okay. So once again, we've got another conflict with units. So this is the volumetric thermal expansion coefficient, or beta. It's not KT, 1 over KT this time. That was the beta in the stat thermo part of the course. This is the beta in the thermodynamics part of the course. This is the volumetric thermal expansion coefficient. This is the one I said was important for dentistry. So here, let's look at what we would expect for an ideal gas. So this is the definition of beta. So it's 1 over volume times the derivative of volume with respect to temperature at constant pressure. So see, it's the thermal expansion, so the change in volume with respect to temperature. So do you see how that's thermal, the temperature piece, expansion is the change in volume. So we're going to take this beta and we're going to operate on the volume equation, nRT over P. So we're taking the derivative of this volume with respect to temperature at constant pressure. So that's pretty easy. We have temperature to the first power, so it's just going to be it's just going to be nR over P, and then we have this 1 over V on the left. So this is our beta for an ideal gas. And if we were to just put in, 1 atmosphere, numbers for that, 1 mole, the volume of a gas, ideal gas at 1 atmosphere, this would be our beta, 0.082 per Kelvin. So it's kind of like a percent, right? It's like 8% for every Kelvin. Okay, 8.2% volume change. So if I have 100 liters, this would drop down by 8.2 liters per degree Kelvin, go up by 8.2 liters per Kelvin. If I had 1 liter, it would only go up by 0.08. Okay, but that's still pretty large, 8% change. Let's look at some of these others. So these tables are from the Atkins book, and I think it's a confusing way to put data in the table. The table says 10 to the 6th beta. And so we need to understand how to understand that. Okay, so the way you write this is that the heading in the table, 10 to the 6th beta, is equal to the number. Okay, so you see that here's the heading, 10 to the 6th beta, and that's equal to this number. So you set that up, and then you can do math on that. You can move the 10 to the 6th to the other side if you want to see what the beta is. So that means that beta is 8.9 times 10 to the minus 6. Can you see how that's kind of confusing? If you look at the table heading, you might think that it's 18.9 times 10 to the 6, but it's not. It's 18.9 divided by 10 to the minus 10 to the 6. So this is the thermal expansion coefficient for silver. So again, it's smaller than an ideal gas. We would not want, and it doesn't make sense, but we would definitely not want a gas filling because it would expand 8% per degree Kelvin, and you drink something hot and it really expands. It would bust your tooth actually. But silver, much better. It's 18.9, roughly 20 times 20 parts per million is another way to say that. Okay, so if your temperature went up 1 million times, it would only expand 20 units. Okay, so aluminum would be worse though. So like if you're a dentist and you're trying to find filling material, you would choose silver over aluminum Gold is better than silver. It's just not very hard. Okay, but you would maybe alloy some metals together that were non-toxic. Iron's not really toxic, so maybe you find an alloy of iron. Silicon's even better, 2.6. So a silicon filling, at least in terms of its expansion coefficient, would be better than the other ones we talked about. Okay, zinc would be terrible compared to those, 30. Right? It would expand 30% more than silver, so you wouldn't want to use that.
Is that also why they use silicon in the backgrounds to?
Oh, the silicon caulk?
Yeah.
No, I don't think that's an expansion issue. Yeah, I think it's just chemically inert. Yeah. I wish it were. I mean, I'm looking for a bathroom caulk that actually has an anti mildew component in the caulk. Like they should make that where it would leach out and kill the mildew, on its own. So that'd be nice product. Okay, then over here the liquids. Notice they're 100 times more expansive. So this would be 18.1 times 10 to the minus 4 per Kelvin. So it would expand 100 times more than the silver. So we wouldn't want to use mercury liquid. Not only that, it's toxic. Okay. And so anyway, and then here's water down here, water liquid, water solid. So, it's going to be 200 in the same sort of order of magnitude as silver. It would be 200, and silver is 20. So it's 10 times more than the silver. Okay, so that's thermal expansion coefficient. So let's look at the isothermal compressibility. So this accounts for the volume change with respect to pressure. So if we press on something, does it squish? How squishy is it? That's a nice way to think about it, right? Because that's the compressibility. So for an ideal gas, we have volume equals nRT over P. And here's our definition of the isothermal compressibility. So it's the change in volume with respect to pressure. Okay. Isothermal means that it's at a constant temperature. Okay. So think about compressibility, right? If you compress something, you press on it and it shrinks. Okay. So that's the dV dP part. So let's operate on our volume equation. Now we're going to set temperature constant. We're going to take the derivative with respect to pressure. So it's P to the minus 1. So minus 1 is going to come out front, and we're going to have P to the minus 2. So the minus 1 came out front, and it canceled this minus sign here. So it's a positive value, and it's P squared in the denominator because it was P to the minus 1. When we took the derivative, it went down to P to the minus 2. And so that's our isothermal compressibility. If we put 1 mole in, room temperature, the volume of a mole at 1 atmosphere, and 1 atmosphere squared, we're going to end up with this 24.1 per bar or 24.4 per atmosphere. So instead of percent, this is like 2,400% per atmosphere. So the volume changes a lot for an ideal gas based on the pressure. If we press on it, it shrinks. If we drop the pressure, it expands. And so let's look at these metals up here. So if we change the pressure on aluminum, how squishy is it? Not very squishy. It's 1 part per million squishy. So silicon oxide's a little more squishy. Oh, sorry. But nickel is even less than aluminum. I'm sorry, I said silver. I meant aluminum. Aluminum is pretty squishy compared to nickel, compared to titanium dioxide. Sodium is very squishy. It's 10 times more squishy than aluminum. Graphite's really good. Doesn't change dimension much at all with respect to pressure. I was talking about hydraulics, and so hydraulic fluid over here, these are again 10 to the minus 6, so they're still pretty good. This is 64 times 10 to the minus 6 per bar. And so, here's a hydrocarbon. We want our hydraulic fluids to be non-reactive with metal, and so a hydrocarbon is good. It's not going to rust the metal like water would. Okay, so we could put hexane into our system, and it would be decent. Something with a big fluffy chlorine on it. Look how squishy those chlorines are. Okay, so there you can see the effect of the chlorines. The oxygens and like ether groups and alcohol groups, those are also pretty compressible. Okay. Water's not very compressible, 45 compared to the 100s. So water would be a better hydraulic fluid in terms of delivering the force without squishing, but it's corrosive. And so if you've got metal in contact with water, and it's going to oxidize, it's going to start to rust. So it's not the best. Mercury would be great, but it's toxic. But we could run a really good hydraulic system using mercury, but it's probably not good from a health and safety standpoint. And an environment, when you have leaks, an environmental standpoint, you're going to be getting mercury all over the place. So there's, it's always a balance, right? You had the performance, so mercury would be the best performance, but safety and environmental impact, not the best. So you always have to balance things. No, she eventually, it was, yeah, but it was complicated. She didn't die from acute radiation poisoning, but she might have died from chronic exposure. Yeah, and they handled some pretty radioactive stuff. Just a side note on that, we've got a little. They had purified radioactive elements from pitch blende, which is kind of like slag from mining operations, and it had a lot of uranium in it. And they had purified polonium enough. It was named after Poland, which was her home country, enough that when they came into their workroom at night before they lit the lanterns, they could see that the little test tube was glowing green. Now, you see the green, you always like Homer Simpson, right? The green thing. What the green color's for real. And it's not anything to do with the radiation. It has to do with nitrogen in the air. So if you ionize nitrogen in the air, the emission of the nitrogen atoms is green. So the atomic emission of nitrogen is green. And so this was so hot that it was ionizing nitrogen, and it was glowing green. So they came in the thing and they both said, stop. And they're looking at their test tube and they could see a green glow. So it's not as bright as the Homer Simpson one, but still it was. So that's actually legit. It goes back to for real observations. And so if you were to see a radioactive source that's glowing green, back away because it's pretty hot. It's ionizing air. Okay, let's talk about the Joule-Thomson coefficient. Now this one's a little confusing because it's the derivative of temperature with respect to pressure at constant enthalpy. Okay, and that's a little bit tricky to measure. We could do it with deltas. Okay, but let's look at this isothermal Joule-Thomson coefficient. So notice up here, this top one is just the Joule-Thomson coefficient. Okay. The isothermal Joule-Thomson coefficient is just got a little t here. See the t here? And it's very simple. It's the Joule-Thomson coefficient times the heat capacity at constant pressure. And this just means molar heat capacity at constant pressure. So let me show you how these are related. So if we were to plot the enthalpy, so look at this three-dimensional plot. We have the enthalpy on the y-axis, the temperature on this axis, the pressure on that axis, and you've got some surface. That is the enthalpy. Like if I raise the temperature, I raise the enthalpy, right? Temperature's going up, enthalpy's going up. The enthalpy with pressure is a confusing piece. You see it goes down here, but then it starts to go up over here. So it's definitely, a little complicated with the enthalpy as a function of pressure. Okay, so we'll see some ramifications of that in a minute. But notice this derivative. So this, maybe you never really thought about derivatives this way, but it's just the instantaneous slope. Right, so at constant temperature, that means we're at a constant temperature on this axis. And this confusing curve here we're going to pick an isotherm. We're going to pick a deal. And this change in enthalpy with respect to pressure is the instantaneous slope right there. You see that line, that black line? That's the tangent, at that point. So that would be the Joule-Thomson coefficient at that temperature and pressure. Okay. The isothermal, no, that's the isothermal Joule-Thomson coefficient. The actual Joule-Thomson coefficient is at constant enthalpy. So how do we pick a constant enthalpy? Well, look here. We pick a spot on the enthalpy axis, and then we look at how it goes on that curve. You see, that would be this curve right here, because wherever this constant enthalpy, it's sort of like a contour plot. We have these different contours at different parts of enthalpy. So think of a weather map. You've got those little contour lines for the pressures. This would be an enthalpy line, and so then the Joule-Thomson coefficient is the instantaneous slope in that direction. So the change in temperature with respect to pressure at constant enthalpy. So this one, this Joule-Thomson coefficient is this red line, but the isothermal Joule-Thomson coefficient is this black line. And they're related to each other by the heat capacity. So if you find one, you can find the other very easily. So it's very easy to measure this one. So this isothermal Joule-Thomson coefficient is easy to measure. So we measure that one. We know the heat capacity at constant pressure. And so we can easily find the Joule-Thomson coefficient. So here's our isothermal Joule-Thomson coefficient. When I was little, we didn't really have this is kind of personal information. We didn't really have the deodorants, the stick or whatever. We had sprays, okay? And I do remember, I wasn't a chemist. I was a little kid, and parents are like, man, you need to start wearing deodorant. You're starting to stink, sixth graders, right? And so we had Right Guard. And I would spray that under my arm and it'd be so cold. I'd be like, dang, I hate that, And I'm thinking, it's not cold in the can. Why is it cold on my armpit? It's this. There's a drop in pressure. It's a high pressure in the can, low pressure outside. You spray it, it cools down. That's refrigeration. That's what's happening. The can's not cold, but when the gas escapes from the high pressure to the low pressure, what happens? Those little water droplets or gas droplets, they spread out. And what do they lose? They lose the intermolecular attractions. And something's got to give, so the temperature gives, right? They lose energy. I'm stripping molecule away from molecule, and all of those hydrogen bonding and associations, they break. And when they break, the temperature of the gas drops. So that's what's going on here. So we run the gas through this porous plug, the temperature drops. And so we have a heater, which we can measure, just like your lab this week. We measure how many joules per second are going into the heater, and we measure how much energy it takes to raise that temperature back up to what it was when the gas was at high pressure. So here's a little calculation. We got a flow rate of 6 moles per minute, the pressure drop of -5 atmospheres. The heater's giving 10 watts to maintain a constant temperature. So here's all the units that work out. We have watts is 10 joules per second, 60 seconds per minute, moles per minute, the per minutes cancel, and we have joules per mole atmosphere, which is the units for our Joule-Thomson coefficient. And then we can swap that around with the heat capacity at constant volume, and we get this Joule-Thomson coefficient of 0.5 K per atmosphere. What happened?
I looked down
Okay.
and there was just
a bunch more numbers. Okay, yeah, and then we're going to run out of time, so let me finish this up. Remember that pressure relationship for the enthalpy was confusing. It wasn't always going down. It turned around and came back up. And that gives us these inversion temperatures. So there's a region where the Joule-Thomson coefficient has greater than 0, which means it's cooling. And there's a region where it's less than 0, which means it's heating. And so we could use these inversion temperature diagrams to decide which gas would be good for refrigeration in a car or for cryogenic refrigeration. So your automobiles, the inside of your car is running, at temperature around 298, room temperature? So nitrogen gas is cooling in that region up to about 400 atmospheres. So in this region, the compressor on your air conditioner would pressurize that nitrogen up, and then when it goes through the little cooling jets, it'll cool down and it'll refrigerate your car. So we've got a nice pressure range in which we can use nitrogen gas in our car to cool. Now, it may not be as efficient as the modern refrigerants, but you could put nitrogen in your automobile's air conditioner. It just might not be as cool as it would be if you had a really high dollar refrigerant, okay? You could not use hydrogen because look here, hydrogen has this range of cooling. And so up above 200 Kelvin, hydrogen would actually heat up. So that's pretty crummy. If you put hydrogen in your air conditioner in your automobile and you turn on the AC, it would heat. That's bad. And the same thing, if you have a hydrogen tank in your car and it springs a leak, it's going to heat up as it escapes. It's going to make the leak worse, perhaps, especially if it's a polymer tank, and the heat would make the polymer weaker. So that's a bad deal. We don't want to run around with hydrogen tanks on our vehicles. It's in my opinion, that's a bad idea. Now, why would something heat up when it escapes? Well, if the average distance between the gases, because you're at high pressure, those gas molecules are close together. When they escape, they release energy. So when you drop the pressure, now the average distance between the gas molecules is maybe out here. And so when they go to that spot, they release energy. So that would be the hydrogen situation or something at too high a pressure. If your average distance is here, then your gases are happy as can be. And when they escape from high pressure to low pressure, you have to put heat in. So those gases cool. So that's the underarm deodorant, the Right Guard. You spray that, it goes from high pressure to low pressure, and when it expands, it has to take heat in or it drops its temperature. If it can't take the heat in, it drops the temperature. So that's what's going on with real gases. We can use this for refrigeration, and here's the guts of different refrigerators and a discussion on the Einstein refrigerator. We're out of time and the grad students are showing up, so let's cut it off now.